Before we can even whisper the famous equation F equals ma, we must first meet its most mysterious component, force. Imagine force as the invisible hand that orchestrates all motion in the universe. It's the ghost in the machine. It's not energy, and it's not power. It's something more fundamental. A force is simply a push or a pull upon an object, resulting from its interaction with another object. But here's where it gets profound. Forces are the causes. They are the reasons why a state of motion changes. Think about it. A book lying on a table remains at rest until the force of your hand interacts with it, compelling it to move. A satellite glides through the void of space, not because it's being propelled, but because it's constantly being pulled by the gravitational force of the Earth, bending its path into a perpetual curve. This leads us to a critical distinction pioneered by Newton himself. Net force. Dot. An object rarely experiences just one force. That book on the table has gravity pulling it down, while the table pushes back up with an equal force. When these forces are balanced, the net force is zero, and nothing changes. Motion only happens when this balance is shattered, when the net force is not zero. This is the gateway. This unbalance is the trigger. It's the moment the universe leans in and whispers, something is about to happen. Understanding this invisible, causal hand is the first and most crucial step to unlocking the secret of motion itself. Now, let's meet the second character in our story, mass. Most of us think of mass as just how much stuff something has, a number we read on a scale. But in the world of physics, and especially in Newton's second law, mass has a soul, and its name is inertia. Inertia, from the Latin word for idleness, is the stubborn resistance of any physical object to a change in its state of motion. This isn't just about moving objects, it's about resting objects too. A massive, heavy boulder is difficult to move from rest because of its immense inertia. It resists your attempt to change its state. Conversely, that same boulder, once rolling, is terrifyingly difficult to stop because its inertia resists the change from motion back to rest. Mass is the numerical value we assign to this inertia. It's the quantitative measure of an object's reluctance to accelerate. So, when we say an object has a mass of 10 kilograms, we're not just saying it has a certain amount of matter. We're saying it possesses a specific quantifiable level of stubbornness against any force that tries to change its speed or direction. This is why a tiny pebble can be flicked away with a finger, while you must summon all your strength to shift a grand piano. The difference isn't just weight, it's the profound intrinsic inertia encoded in their mass. With force as the cause and mass as the resistance, we now arrive at the effect, acceleration. This is the moment of change, the result of the cosmic tug-of-war. Most people think acceleration just means speeding up, but in physics, it holds a much more elegant and powerful meaning. Acceleration is the rate at which an object's velocity changes. And velocity, crucially, is speed with a direction. This means that acceleration occurs whenever there is a change in speed, a change in direction, or both. When you press the gas pedal in your car and your speed increases, you are accelerating. When you slam on the brakes and your speed decreases, you are accelerating. We call this deceleration, but most beautifully, When you drive around a curve at a constant speed, you are still accelerating because your direction is continuously changing. This is the centripetal force at work, constantly pulling you toward the center of the curve. Acceleration is the art of change itself. It is the universe's dynamic response to an unbalanced force, a response that is intricately shaped by the object's mass. It is not merely a number, but a story, the story of how an object's journey through space and time is being rewritten, moment by moment, by the invisible forces acting upon it. Now, we arrive at the summit. We have our three protagonists: the cause, force; the resistance, mass; and the effect, acceleration. Isaac Newton's genius was in weaving them together into a single, breathtakingly simple, and universally powerful mathematical tapestry. F equals ma. This is not just a formula to memorize. It is a statement of cosmic truth. Let's read what it says. First, it tells us that acceleration is directly proportional to the net force. This means if you double the net force acting on an object, you will double its acceleration, provided the mass stays the same. A team of two horses can pull a carriage twice as fast as a single horse. Second, and equally important, the law states that acceleration is inversely proportional to the mass. This means if you double the mass of an object, you will cut its acceleration in half, provided the force remains the same. Shove a shopping cart and it zips away. Shove a car with the same force and it barely creeps. The equation F equals ma is the ultimate balance sheet of motion. It quantifies the precise trade-off between the effort we apply, the inertia we must overcome, and the change we ultimately achieve. It is the rule book that every moving object, from a falling leaf to a spinning galaxy, is bound to obey. Now that we've mastered the fundamental equation, F equals ma, let's pull back the curtain on what F really means in complex situations. In the real world, objects rarely experience just one force. They exist in an intricate web of simultaneous pushes and pulls. This is where we introduce our most powerful tool, the free body diagram. Imagine isolating an object and drawing every single force acting upon it. As an arrow pointing in the direction the force is applied. The length of each arrow represents the magnitude of the force. A book resting on a table, we draw gravity pulling down and the normal force pushing up. A car accelerating, we draw engine force forward, friction backward, gravity down, and normal force up. The true power of F equals ma reveals itself when we understand that the F in the equation is actually the vector sum of all these forces, the net force. When arrows point in opposite directions, they cancel each other out. When one arrow is longer than others, there's a remainder that determines the acceleration. This visual representation transforms complex situations into solvable puzzles, allowing us to see the invisible web of forces governing every motion and precisely calculate how an object will respond to the symphony of influences acting upon it. Let's now witness the true power of F equals ma as we apply it to revolutionize our understanding of everyday phenomena. Consider car safety design. During a collision, the goal is to minimize the force on passengers. Since F equals ma is fixed, mass doesn't change, deceleration is inevitable. Engineers manipulate time and distance. Crumple zones extend the crash duration, reducing the acceleration a, which dramatically decreases the fatal force F on occupants. Now look at rocket science. A rocket's mass, m, constantly decreases as fuel burns. To achieve constant acceleration, a, with a diminishing mass, the thrust force F must be absolutely colossal, hence the fiery, powerful engines. Even in sports, when a soccer player kicks a ball, their foot applies force F to mass m, creating acceleration a that launches it toward the goal. From the delicate flight of a butterfly to the monumental orbit of planets, F equals ma serves as the universal translator, decoding the hidden language of motion in everything we see. This equation doesn't just live in textbooks. It's the silent architect of our physical reality, explaining why seatbelts save lives, why rockets reach space, and why a perfectly executed kick can change the outcome of a game. The true test of understanding F equals ma lies in wielding it to predict the unknown. This is where we become cosmic accountants, balancing the books of force, mass, and acceleration. Let's develop our problem-solving toolkit through a clear, step-by-step methodology. First, identify the system and all forces acting on it, sketching a free body diagram to visualize the network of influences. Second, calculate the net force, F net, by adding all forces as vectors, considering both magnitude and direction. Third, write the equation F net equals m times a with the net force on one side and the mass acceleration product on the other. Fourth, solve for the unknown, whether it's finding acceleration given force and mass, determining force from mass and acceleration, or calculating mass when force and acceleration are known. Let's work through a classic problem. What acceleration does a 500-kilogram car experience when the engine provides 1,500 newtons of force and friction opposes with 500 newtons? Net force equals 1,500 newtons minus 500 newtons equals 1,000 newtons. Then, 1,000 newtons equals 500 kilograms times A, giving us A equals 2 meters per second squared. Through repeated application of this disciplined approach, we transform abstract theory into concrete predictive power, enabling us to mathematically anticipate how any object will move under any set of forces. Just when we've mastered F equals ma, we must recognize that our journey has only begun. This powerful equation has boundaries, and beyond them lies even more profound truth. First, we encounter variable mass systems, rockets that lose mass as they burn fuel, requiring us to use calculus as mass becomes a function of time. F equals dv over dt. Then we discover that F equals ma is actually a special case of Newton's second law, expressed in its general form. Force equals the rate of change of momentum, F equals dp over dt, where momentum p equals m times v. This general form handles situations where mass changes, making it universally applicable. Most mind-bending of all, we eventually reach the frontiers where Newtonian physics itself breaks down. At velocities approaching light speed, Einstein's theory of relativity reveals that mass isn't constant and F equals ma fails, replaced by more complex equations. In the quantum realm of subatomic particles, the very concepts of force and deterministic motion dissolve into probability waves. F equals ma isn't the final word on motion, but rather the brilliant foundation upon which modern physics was built. The perfect starting point for a journey that leads to the outer edges of our understanding of the cosmos. reminding us that every law of nature, no matter how fundamental, points toward deeper mysteries waiting to be explored. As we conclude our journey through Newton's second law, we see that F equals ma is more than an equation. It's a philosophical masterpiece. It teaches us that change requires both a driving force and the willingness to overcome inertia. It shows us that multiple influences must be resolved into a single, decisive direction. And it reminds us that even the most fundamental truths have horizons beyond which new wonders await. This is the legacy of Newton's second law. Not just a tool for calculation, but a lens through which we can view the hidden mechanics of our universe, from the fall of an apple to the dance of galaxies.